Before the lecture begins, we would like to invite Dr. Andrew Wang from Academia Sinica to introduce the topic of the day and help us know more about the topic. 在正式演讲开始之前，我们很荣幸邀请到中央研究院王惠君院士进行会前导读。王院士将利用15分钟时间介绍本次演讲主题，帮助各位更了解今日的演讲内容。请掌声欢迎王院士。
这个他们没有给我解释清楚，所以我以为只是要来介绍我们的讲者而已哈。所以怎么忽然跑出一个15分钟的这个导读哈？所以我要随机应变一下来想一想看看哈。不过我还是这样子好了，从这个我们今天诺贝尔奖主哈这个他叫 Aaron Ciechanover 哈。来介绍一下哈 ，Ciechanover 他是现在应该我不知道他退休了没有，不过他原来在这个 Technion 这个当教授哈。那等一下会看看他的一些sorry I have to speak in English I forgot so I will introduce Aaron I know him for a long time and so as you can see, he was born in Haifa. At that time, it was not Israel yet. But in any event, in 1947, in Haifa. And later on, he studied medicine and got an MD degree, as well as a master degree from the Hadash Medical School. And later on, he joined Technion. Technion, of course, is one of the best science and technology university in the world. He, as you may not know, that Technion, if I remember correctly, that they have a kind of branch in New York City to do investment, and it's one of the largest investment ventures in the world. So you can see that Technion not only strong in the basic science and so on, but its application in various areas is also enormous. In any event, he got the degree from Technion in 1981, and later on, I didn't put it here, he went to MIT to study with Harvey Lodish for a couple of years as a postdoc. And then later on, he I believe returned to Israel and to continue his study in biochemistry. And one of the hallmark of his achievement, of course, was that he got a Nobel Prize in chemistry in 2004. That was 20 years ago. So let me see. Oh, here. Here's Aaron. Okay. In the middle. Now I put this slides because he's an international advisory member of Tang Prize Foundation, and so this year we are reviewing the candidates and so on. And he helped us to bring a lot of input. And this is Zheng Chuanxiong. He is from Taida, but he's the CEO of Tang Prize, not only in biopharmaceutical, but Tang Prize, as you know, has four categories. And so he's the CEO of Tang Prize committee. And this is Wenchang Chang, Zhang Wenchang Yuan Si. He is the chair of our biopharmaceutical prize. And so over the years, Tang Prize, of course, become more and more prominent, and those international advisors play a very important role for us. And this is him in lectures. I met him several times, of course, in the international meetings, and he's a very lively lecturer, as you will see later. Okay, so here, after his postdoc research returned to Israel, he worked on some very basic biochemistry work. Okay, that's very fundamental. And at the beginning, of course, when we scientists do the research work, we don't think about application too much, at least in the beginning. But the time has changed. So, so because of his work, over the years, he received numerous important international prizes. And as you can see here, the Lasker Award in basic medical research is usually a forefront of Nobel Prize. So many, I don't know what the percentage is, but maybe 40-50% of the Lasker Award winners became Nobel Prize winner later on. Okay, and of course in 2003 he obtained the Israel Prize, and as we all know that he was awarded a Nobel Prize in chemistry. And the award was for his discovery, I think with also his boss and colleagues, the ubiquitin-mediated protein degradation. And I'll give a couple description of what a ubiquitin, for those who is not a biochemist. Ubiquitin is a small protein molecule later on, as you will see. But in any event, he made a very important discovery that how the proteins are metabolized or degraded back into amino acids. So for this kind of discovery, it has so wide implications in, for example, the homeostasis of cells and involved in the progression of many diseases and so on, if it's not functioned properly. So this is, I think, his hallmark, and as you will see later on that he has made many other important discoveries. So he obtained many other prizes. For example, let me show you. He is foreign members of our National Academy of Sciences, National Academy of Medicine from the United States, since he's not a citizen of the United States, so he is a foreign member, okay? And so, of course, in Taiwan, Cheng Kung University offered him an honorary Doctor of Science degree. Now, I'm not sure why he went to Cambodia. And Cambodia is a very interesting country anyway. 我们这个什么小鸡现在被关在那里哦。Anyway, in 2011, he got also the Humboldt from the Humboldt Foundation, the Humboldt Prize, and so on. Finally, or more recently, not finally, he is also elected as the German Academy of Sciences. So those are his, some of the awards he obtained. But today I also want to mention something because his lecture title says something about diseases. And he, of course, has been involved in many scientific advisory board of biotech companies. And if to tell the truth, I'm not exactly sure what each of the companies is doing, but we can ask him later on, okay? So, and he's also a member of the advisory board of this Patient Innovation, a nonprofit international multilingual free venue of patients and so on and so on. So he made a lot of important contributions, and okay, so here is some of the kind of abstract I need to describe to you. How is his contribution? Now, his discovery, the first discovery, was published in a journal we call it BBRC. It's Biochemical and Biophysical Research Communication. And nowadays, we treat it as a okay journal, okay? We normally don't publish our most important paper in this kind of journal. But here, what I want to point it out to you is nowadays we all evaluated or judged by how many NSC paper. You know what an NSC paper is? A Nature, Science, and Cells paper if you are in biological science. Now NSC, of course, is the old 国科会. So NSC judge us by those publications. But I think what he may tell you that whether or not you publish your paper in the sort of very high impact factor, like New England Journal of Medicine nowadays, do you know how many impact factor points is nowadays? It's like 35. It's totally ridiculous. But in any event, he published his paper, first important paper, about the proteolytic importance of ubiquitin, okay? And his name was sort of misspelled because of some, but no matter, he is still Ciechanover. Okay, so with Hershko, he published several other important papers. Those are the foundation of his Nobel Prize. Okay, so don't get in this mess of high impact factor paper. Yeah, it's only, I don't know what BBRC nowadays, maybe 5.0. Anyway, so his important discoveries on this little molecule, okay, a small protein, maybe 70 amino acids or so, and it's a protein. It's actually quite stable, and it has noticed that several lysines on it. Okay, it started with the N-terminal with some beta sheet here, and we're covered with the alpha helix. And actually, my friend from MIT, he used this so-called split ubiquitin as a tag to study protein-protein interaction. But in any event, this small protein plays important role in this pathway, the protein degradation pathway. But the first thing the cell does is to mark the protein a cell wants to degrade by putting ubiquitin on it. But it does not put just one ubiquitin, it put several ubiquitins, so we call it a polyubiquitination, okay? So this is a signal, I got it. A signal that tells the cell that I need to degrade certain protein, and this just put a substrate here. Now, this process requires energy. It needs to use ATP to hydrolyze and get energy and go through this process. Now, many of the ATP, there's a very important social event nowadays. We have this toxin that intoxicate the person by blocking the translocase of ATP in the mitochondria. You lost the energy because of this process. That's why your multiple organ got paralyzed. It could not function. So ATP is an important source of energy, and it also requires in this ubiquitin formation. Polyubiquitination formation, okay? So this is a truly important step or process in the cell and to maintain the homeostasis and many other. So if this process is a malfunction, then you get a lot of diseases, okay? So how does protein get degraded? Well, there are many other ways, but the most important one is the so-called proteasome. Proteasome means collection of proteins. So proteasome is a large multi-subunit complex, okay? And this structure solved by X-ray diffraction, I believe. But in any event, you can see that it's a very large complex, and with some cavity in the middle. So it was sensed that the protein is ubiquitinated and put it in. Here is a schematic. Darn it. Okay, sorry about that. A schematic how the proteasome works. Okay, so as you can see that you have to first recognize, or this complex has first recognize the ubiquitinated protein and put it in. You can see here as a ubiquitin. As a few sphere here, and put it in and unfold it, and then inside the proteasome there are a number of proteolytic enzymes got involved, and it will digest the protein or the substrate, we call it, into amino acid and return it to the cell for to use it again. Okay, so this is the kind of basic concept of this protein degradation, and involve the proteasome systems, and it's very important. So let's see what Aaron will do, and he will give us this very impressive title called "The Revolution of Personalized Medicine." So I believe I was promised to be given his slides in advance, but NTU didn't do that for me. So I don't know what he's going to talk about. But in any event, he's going to talk about a number of keywords, so-called personalized medicine or precision medicine and so on. But the important question is the following. Are we going to cure all diseases, and at what cost? And the answer is to be or not to be. And in Chinese, we call it 大哉问. So we will try to find the answer from Aaron. Are we going to cure it or not? We'll see. Okay, here is it.
Thank you so much, Dr. Andrew Wong. So, ladies and gentlemen, welcome to the National Taiwan University Royal Palm Lecture Series. Let's first welcome the host of today's events, Dr. Chen Wenzhang, the president of National Taiwan University, to deliver his opening remarks.
Dr. Aaron Ciechanover, and also our vice president and the faculty and the students, good morning. As the president of National Taiwan University, I would like to welcome Dr. Ciechanover to give the speech. Our Royal Palm lectures entitled, I think it's there, the revolution of personalized medicine. Are we going to cure all the disease, and at what price? Well, I think I have a good memory to remember that. Anyway, it's my great pleasure to introduce Dr. Ciechanover. He's a Nobel Prize winner in 2004 in the area of chemistry. Actually, he is in College of Medicine, but he won a Nobel Prize in the area of chemistry. He received a doctorate degree in 1982 from Technion, the Israeli Institute of Technology. At that time, he worked in ubiquitin with his supervisor, Hershko, and in collaboration with one of the cancer center in Philadelphia, Dr. Rose. And because of their discovery on the unique ubiquitin, I think that their mechanism, and after that, those three of them, they won the Nobel Prize in 2004. And after that, he did spend his time as a postdoc in MIT and continued to his work in the ubiquitin, and he found out the relation between the ubiquitin with the cellulose system and also the cancer disease, the tumor, those kind of issues. And because of their discovery, a lot of medicine was discovered. and cure a lot of, I think save a lot of life in the world. Therefore, his achievement won Nobel Prize. And not only that, he also worked with as a member of Israel Academy of Science and also National Academy of Science in the United States and other honors. So I'm very happy to have him here. And I just asked him this morning, maybe this is the second time for him to visit NTU. Quite a few years ago, he did visit NTU for the Wang Guangcan lectureship in bioorganic chemistry, I believe, a few years ago. And he also is an international advisory board member of Tang Prize. And I very appreciate for the introduction of Executive Director, Professor Chen Zhenchuan, Professor. And because of him, we have Dr. Ciechanover to have here to give the long term lectures. This is the sixth time we have this kind of lecture. This is the highest honor lecture in NTU. Previously, we have the Nobel Prize winner in physics, the Amano Sensei. And after that, we have the academician, Philip Liu, and the president of University of Tokyo, and also that the president from University of Tsukuba. So anyway, this is the fifth time. I did not remember correctly. Anyway, I believe his lecture will be very enjoyable, and we can learn a lot about ubiquitin from his discovery since he was a graduate student. And we will benefit a lot from his lecture, and please join me to welcome him. Thank you very much. Thank you.
Thank you, Dr. Chen, for your wonderful remarks. 谢谢陈校长的致辞. Now, ladies and gentlemen, please join me in welcoming our speaker, Dr. Aaron Ciechanover. 各位先生、女士，请掌声欢迎今日的讲者 Aaron Ciechanover 博士。
Okay, good morning, everybody. Good morning. The people who spoke before me gave an introduction to the ubiquitin system, so I don't have to speak about it. Actually, I didn't intend even to speak about it. Just to sum up, since I'm coming from two worlds, I'm a surgeon by education, but then I moved to biochemistry. So I'm speaking, I would say, two languages, the language of medicine and also the language of science. So this lecture will be devoted to medicine rather than to my science. But the system that we discovered and I'm still working on, I have a very big laboratory, we are very active. We are developing now a new drug, we have a company, and we are very close to clinical trials now on patients, is a quality control system that takes care of two types of proteins, either damaged proteins, like misfolded, mutated, denatured proteins, or healthy proteins that are not needed anymore, that they completed their function. For example, in the cell cycle, there are cyclin-dependent kinase, cyclin-dependent kinase inhibitors, and so on and so forth, that they are not needed anymore, and the way that the cell chose is not to inactivate them by reversible way like phosphorylation, but rather to get rid of them, to degrade them, because this really ascertains unidirectionality. There are many processes. They are so important that you really have to ascertain unidirectionality, and the best way is, of course, to get rid of the protein that is regulating them, because if you phosphorylate, somehow it can be dephosphorylated, and then the cell can be stuck, for example, in the middle of DNA replication, and then it will be a disaster. So, as a result of our discovery, several drugs have been developed. They are already in the market. They are being used all over the world, mostly for malignancies, multiple myeloma and other diseases. They are very successful drugs. They have completely changed the clinical landscape of the disease. I remember myself as a student and as a physician. You know, multiple myeloma is a B-cell leukemia or B-cell lymphoma. People died within 1 year in suffering. Now many of them are completely cured. And most of them are enjoying 10 and 15 years of life in healthy condition, in high quality of life. So they really did revolutionize the way that we look at these malignancies. And on the way are also neurodegenerative diseases like Alzheimer's, Parkinson, ALS, Huntington, and so on, because these are all diseases of quality control of proteins. You know, the hallmark of all neurodegenerative diseases is accumulation of aggregated proteins in the brain. The proteins are different from disease to disease. They're also different from the site of their precipitation, but the principle is the same. And I believe that once one disease will hit, the rest will fall apart. So that's about the ubiquitin system. Of course, as a physician, you look at patients one by one. I remember when I was a surgeon, you are operating one patient, and then another patient, and then another patient, which is very rewarding, but if you are lucky enough in science, you can impact the lives of millions of people without even knowing them. You don't know the names, but by developing a drug, you can have an impact on the lives of millions of people, and in that sense, I think I was lucky. So that's for the ubiquitin system, but I want to change gears and to move to a major revolution that medicine is undergoing these days, and that's the revolution of personalized medicine. I want to talk about what I see as the lecture is very personal lecture. It's my lecture. So that's the way I view it, but you know, many people view the same. Some have different views. And I want to talk about the historical roots of this revolution, why now, and then about the price we are going to pay, what are going to be the implications of this revolution. So we are here. This is the city of Haifa, my city. There is a beautiful garden of the Baha'i garden where they buried their leaders. Actually, they were persecuted in Iran, and they smuggled the body of the leader to Israel, and they buried him in a beautiful garden. It's a UNESCO heritage site. And the medical school is here. We are on the bay. It's basically here. We don't see it. And it's part of a big technological university, the Technion, which is one of the premier technological universities in the world. We have about 3 Nobel Prize winners on site. Several of our graduates won the Nobel Prize. It's a very good university. So what is our dream? Our dream is to remain young and beautiful, but more than that, to remain healthy. And to remain healthy, we need to cure all diseases. So you see, people thought about it. It's not my original idea. So the question is whether this is possible at all. Well, let's look at history. I think that history is the only thing that we can look at. And the history tells us the following. About 120 years ago, 124 years ago, at the turn of the 19th century into the 20th century, people were living about 50 years. People died of infection. There was no antibiotics. There was no X-ray, not to say CAT scan or MRI. Basically no surgery. You know, anesthesiology was like very marginal. Operations were infectious, very painful. So no imaging. And we didn't understand much about life. We didn't understand about cholesterol. We didn't understand biochemistry. People died of infection in the field during wars. And mostly, we didn't have communication. Think that, you know, though communication is not a medical device, the way that we can communicate, not by physical lectures, by the internet, by publication, the culture of publication. You know, initially it was printed journals. Now we are doing it via the internet. Really revolutionized the way that we are doing science these days. You publish a paper, the minute the paper is out, it's the same minute that everybody in the world can see it, in the same very minute. So, and now even we have the ArchiveX, so we can even publish before we publish. So, so this is kind of an oxymoron, that something is published before it's being published. So, but nevertheless, the world of communication was not there 120 years ago, so medicine was very limited. China was China, Japan was Japan, everybody worked for himself. People traveled by ship, and even that was impossible. We didn't fly at all. There was no flights. So remember, it's only 124 years ago. So at that time, people were living 45 to 50 years. If we go back 4,000 years ago to the first Chinese dynasties, to the old Romans, to the Greeks, they lived about 35 years ago. 35 years on the average. You know, Queen Cleopatra, King Ramses, Archimedes, Socrates, all this, Julius Caesar. At that days, 4,000 years ago, the lifespan was about 35 years ago. So it took about 4,000 years, from 4,000 years ago all the way to the turn of the 20th century to extend life by maybe 15 years. And then in one century, one single century, the 20th century, we extended life by 35 years. On the average, I don't know what is the exact lifespan in Taiwan. I assume it's around 85, more or less. Maybe 85 for women, 83 for men. In all the OECD countries, it's about the same. We extended life by 35 years. So we added like 60% to the lifespan of 125 years ago. Wow, that's amazing, 60%. So first of all, how did it happen? Well, it happened because of science and technology, no doubt about it. It's antibiotics, it's vaccination, it's imaging, it's clean water, sewage system, understanding diet, biology, engineering, whatever you want. It's all science and technology. The politicians, unfortunately, don't understand it, but all the knowledge coming from one place. It's called a university. You know, it's a strange institute where young students are learning and researchers are doing research, but all this is due to knowledge accumulated and expanded and sprouted out of universities. So in my opinion, university is probably the most important institution that people have ever created. So are we expecting the same trend also in the current century? Is it that at the end of the 21st century we are going to live, well, 60% over 80 is about 50 years, so are we going to live about 130, 140 years in 80 years from now? And are we going to be healthier? The answer is probably not. The answer is probably not. We are approaching a plateau. We are still expanding. We are still extending our lifespan by few weeks every year. So we are coming up. And what happens if we look at the history of medicine, we added the three main killers of Western civilizations were added in the last century. So about 120 years ago, people didn't die of heart attack, simply because they didn't live long enough to get heart attack or heart diseases. Well, people die from time to time. You know, football players, you read in the newspaper that they collapsed during the game and died, but that's very rare. Typically, cardiovascular and vascular diseases are diseases of more advanced age. So they are above 50 or so. Malignancies, cancer. Within people, you know, there is childhood malignancies, but they are about 2 to 3% of all cases. Mostly malignancies are age-dependent, bona fide age-dependent diseases. You know, the slope is, you know, stepping up, you know, above the age of 50, 60. The same for brain diseases. Young people don't get Alzheimer or Parkinson, very rare. So basically, by extension of life, by this miraculous extension of life beyond 50, we floated up diseases that we didn't know about before. And why? Because the biological system cannot sustain the biological machine for so long. These are all degenerative diseases. You know, if you want to look at it from 30,000 feet, all the main killers that we are devoting most of our time learning in medical schools are the inability of biological system to sustain themselves for so long. You know, they are all degenerative diseases. So we are coping with them. Somehow mechanically, you know, we are going into the coronary artery and putting stents, but we don't solve the basic problem. We are trying to inhibit, you know, synthesis of cholesterol by statin, but when we discover it, it's too late. We are trying to do good things. We are trying to develop anti-cancer drug, and probably we'll be able to postpone and to make cancer more chronic disease. Brain diseases, we are still wandering in the desert. We are still not there. But we might get there. And then once we are extending life further and we are pushing towards 100 and 110, maybe new diseases will come. We don't know. Like all these three killers came up, we don't know. But even if there will be no new diseases, because now we know the human genome, I think that the biological systems will not be able to sustain ourselves. You know, we might really rely on gene editing. We might be able to rely on transplantation, but that will be limited at the end of the day. And certainly, once we are talking on the brain, we are not going to do brain transplantation. Not because it's, well, I don't know if mechanically or technically it will be impossible. Maybe we shall solve the technical issues. But I think that if my brain will be replaced with a new brain, it will not be me anymore. So, there are lots of issues, We can replace mechanical organs. We can replace the heart. We can replace kidney. We can replace the lung, the pancreas. We can do it on organs that carry out cell biological and physiological functions. But we cannot replace, I think also ethically, organs that really reflect what we are as human beings. That's beyond our imagination, and it may even risk the very existence of the society as a society. So it has huge implications. But we shall be able, I think, to extend life, for another 10, 15, 20 years. The issue is, of course, not only health-wise, the issue is also economic. Remember, we are retiring, I don't know about Taiwan, at the age of 65, 68, 67. And then we have another 30 years, more or less, to live, and what we are doing there. I mean, what to do? So people talking about, retirement age was set by Bismarck, the old German Caesar, emperor at that time, because at that time, he didn't believe that people will make it to 65. So he put kind of an upper limit on the age of retirement. But nowadays, 65 is young. I mean, people are running marathon at the age of 65. So retiring at the age of 65 doesn't make sense, and many people find themselves very bored at that age, and they are very healthy. And not only that, because they are stopping making money, and they are relying on the pension in developed countries, the pension fund is going to dwindle, because we are living longer and longer, and we are wasting what we are accumulating during the pension fund. So there will be no money left in the pension fund, especially if you look at the Social Security in the United States. They are very much concerned about the young generation, and they might have to increase the part of the salary that is going into Social Security in order to be able to sustain, I would say, humane life after retirement. And also, there is another issue. As I mentioned, the three main killers are age-dependent ones. So we are spending about 90% of our health insurance during the last 10 years of our life. So we need institution, we need intensive care units, we need oncologists, we need help, we need caregivers, we need a lot of help around us once we get kind of older. So we are paying a lot of money during our lifetime for health insurance, and we need some help. I went to the hospital for a few days for some hernia operation or for something minor, but all in all, until the age of 70, 75, we are doing okay, most of us. And then during the last 10, 15 years to our life, we are really, when we don't make any money, we are spending about 80% or 85% of the total health expenditures that we spent all around our lives. So the disproportion here is going to dwindle, and as long as we live, and if we are going to live longer and longer, we are going to spend more and more. And again, this is a bad sign for economy, because all the health insurance funds are going also to be dwindled, not talking about the pension funds. So now there is health and there is pension. These are two different economic entities. So while science and technology have been able to extend our life, side by side, many problems were floated. Not that anybody of us will give up on living long. We all want to live infinitely. But nevertheless, if we think about diseases and we think about economy, there are still major problems to be solved. So it's not just, okay, let's age and be happy and have grandchildren and everything, and everybody will smile. It's much more heavier than that. Okay, so medicine is going in several directions, as you all know, and I'm going to concentrate only on one, on drugs, and drugs are still the major one, but we are going also to artificial organs, and we are going to artificial organs based on two technologies. Ones are real artificial, engineering, joints made of platinum, heart valves made of plastic, and so on, but also stem cell biology. Stem cell biology is still not there. gradually we are doing some progress, but we are, I think, more than 10 years after the Nobel Prize on stem cell by Nakayama and so on, but we are still not there. It will come, there is no doubt it will come, the ability to take cells and to engineer them. But even for simple diseases like Parkinson's disease or even diabetes, replacing the beta cells, we are still not there. We don't have a cure to diabetes now that is based on regulated glucose level, regulated beta cells that will secrete insulin in response to glucose level. We are not there yet. So, but hopefully it will come. So this will be what we call genetic engineering. It's not the classical engineering that we are learning in schools of engineering, but it will be genetic engineering. So that's the two directions that medicine is going besides drugs. So, and of course we are doing better in imaging and so on and so forth. So let's talk about drugs. So the first era of drugs were era of incidental discovery. So penicillin, the first antibiotic that really changed the world in a big way, was discovered completely by coincidence, and it was discovered by Sir Alexander Fleming, who got the Nobel Prize for it. And here he is on a stand, and here you have a petri dish, and in the summer of 1921 he seeded a petri dish that these are the bacteria that has a nutritious media on it, the agar, which is a very heavy nutrient, and he forgot to put the dish in the incubator, and mostly he forgot to put it covered. He left it open in the air. And in the air, the air is contaminated. There are spores of fungi that are flying around, and along the weekend, a spore of fungus, penicillium, fell on the dish. Since it's a nutritious dish, the whole colony grew. He came on Monday, and he found this white colony. So typically it happens to every lab. It happens in our lab too, because we are doing a lot of cloning. So, and we take this dish and we kick it out. We garbage it. But not Fleming. Fleming had good eyes, and he saw a halo here. You see that the bacteria, the smear of the bacteria didn't grow all the way to the border of the colony. And he surmised that the fungus is secreting a material that he called antibiotics. Anti, against. Bios, life. Biology is the profession of life sciences. And indeed, he was not a chemist, by two other chemists, Ernst Chain and Howard Florey. Took them about 10 years, isolated indeed antibiotics that was secreted by this colony, and it's called penicillin, because it was secreted by penicillin. And then it was a principle: if one fungus can secrete one antibiotic, maybe another fungus can secrete another antibiotic. And indeed, Selman Waxman in New Jersey, in Rutgers University, isolated streptomycin from streptomyces, and so on and so forth, and the world changed forever. Penicillin was first used during World War II, during the invasion to Normandy, treating thousands and thousands of soldiers that their lives were saved, because people were dying of simple infection. Every simple bacterial infection killed people. So this was the major reason of death until antibiotic came to the world. And you see, this is serendipity. He forgot the dish. I mean, he didn't know anything about antibiotics. So we cannot rely on serendipity in science. So the world moved to the second stage. And the second stage is high throughput screening. How the second stage, every stage has to mature in order to get into it. It's not that people decided, penicillin was serendipitous, let's do something better. You need maturation of methodology in order to move to the next step. So what was maturing for the next step? Two technologies. One, modeling of diseases by tissue culture. We are able to grow cells of many diseases. Two, chemistry. Chemistry is very important because organic chemists can synthesize now basically almost any material, and on the way they have intermediates. So in order to get from material A to material Z, you have intermediate B and C and D and E. And those intermediates were accumulated into libraries. You can make libraries of millions of compounds on the way. So what people do, they say, okay, let's have a marriage. Let's marry the chemicals with the disease models. It's a brute force, a non-intelligent approach, but nevertheless efficient. They say, let's screen all the materials on the disease model. So in cancer, for example, cells are dividing, right? They are dividing in an uncontrolled manner. So let's take million materials on cancer cells in little wells and see which one can inhibit the growth. Or let's take cholesterol, secreting cells, and try different materials until we'll find one that inhibits the secretion of cholesterol, which is the lipid that accumulates in the coronary artery and causing heart attack, okay? This is not a drug yet, it's a lead, but at least we have something to hold on to. So they developed robotic system, we are growing cells in multiple wells, they are growing in the incubator takes the dish out, the same, another arm of the robot brings the materials, put them on the cells, the cells go back to the incubator, the next day they are going out of the incubator, they go to the microscope can scan them automatically. In all the drug developing companies, in all the pharma companies, you will find these screening devices, and drugs can be, the beginning of a development of a drug can rely on this screening. Again, there is no mechanism in mind, but the idea is that among millions of compounds, one will lock itself into the pathologic protein and will inhibit it or accelerate it, depends on what we are looking for. I'm going back, okay. So indeed, statins, the inhibitors of cholesterol, were developed this way by a pharmacist in Japan, Akira Endo. He worked in a pharmacological company, and he screened a library of 100,000 Japanese plant products, chemicals that were isolated from plants, for inhibition of cholesterol synthesis, and indeed he found that one of them, statin, is inhibiting the pathway that leads from acetyl-CoA all the way to cholesterol, inhibiting a specific enzyme called HMG-CoA reductase. And statin became a blockbuster. So the patent was bought by an American company, by Park Davis, and they started to develop statins, and statins are being used today by millions and millions of people worldwide, and to inhibit the biosynthesis of cholesterol and to prevent heart attack. It's a multi-billion-dollar selling drug. Last year sales were more than $40 billion. It's a huge blockbuster, and it was developed by screening. There was no mechanism in mind, nothing. So, but it's a very efficient one. It's a very cumbersome procedure. It takes years to develop such a drug, but nevertheless, it became very useful. Now, what's bad about it? What's bad about it is that there are several things that are bad. One, there is no mechanism. So we don't know anything about the final drug and about the target. We are looking for something that inhibits a process. Two, the models are very bad. Cells are not human beings, and even mice are not human beings. Human beings are very different from one another. Actually, there are not two human beings that walk on the face of Earth that are identical to one another. People may argue, yes, but identical twins are identical. No, identical twins are not identical, because there is epigenetics. So they grow differently. Once they are out of the uterus, one is eating rice in Taiwan, another one is eating falafel in Israel, another one is eating dirty hamburger in McDonald's in New York. They are exposed to different weathers, different everything. So we are very different from one another, and therefore no wonder that the same disease in two persons is not the same. So you can say, oh, two women have breast cancer, but no, it's not the same. It's two women, and the breast cancer is different from one to another. So therefore, we needed to develop a new method, but again, we needed the tool. And the new method of drug development is called personalized medicine. Actually, we call it the 4 Ps system. 4 Ps because it's personalized or precise, it's predictive, we can predict the future of the patient, even if the patient is not sick yet, by sequencing the DNA. If we can predict, we might be able to prevent a disease that is coming. And mostly and ethically, it's participatory. Patients are taking part in their decision-making process. You know, when I was a young medical student and a young doctor was God. You know, whatever the doctor told you, you should have done. You know, I'm your doctor, so listen to me and don't come with your own nonsense. There is a joke that tells what is the difference between God and doctor. That God does not think that he is a doctor. So, but things have changed because of knowledge and because of, you know, groups and the internet. Patients are much more knowledgeable, they have an opinion, and the doctor is now kind of a consultant. The doctor can say, I can advise you, but you can do whatever you think is appropriate. I am not telling you what to do, I can just give you the background, you can go and ask another doctor, you can do whatever you like. So that's about medicine. So what prompted it? Prompted it the observation that if we have in the same day a group of patients that have breast cancer or prostate cancer or heart attack or anything, these patients have a color, you know, green, blue, and orange. The problem is that we cannot see the color. We don't see the color. We can see the color only after 5 days, after 5 years. We give them a treatment, and after 5 years they divide. Some of them die, unfortunately, and some of them make it. Same disease, same prostate cancer, but different fate, very different fate. And those that are living, some of them are cured, and some of them are chronically going down. So why? Because we couldn't see the color. We couldn't predict. We didn't have a tool to predict. But now we can predict, at least partially. And that, how did it happen? It happened, and that's just the difference. Why we don't have the same disease. It happened because of these two people, Watson and Crick. They discovered, of course, the double helix, and that opened the road to an unbelievable development. You know, people are joking from time to time, oh, you got a Nobel Prize. You know, even within Nobel Prizes, you can tell that some Nobel Prizes are more important than others. In my opinion, I'm not a physicist, so I cannot talk about Nobel Prizes in physics. And though I got the Nobel Prize in chemistry, I must tell you that I never took any chemistry course because I was a medical student. But I can tell you that in medicine, and maybe in chemistry, the most important Nobel Prize is the discovery of the double helix. There is no doubt about it. All our understanding of biology is relying on it. Mutations, genetics, development, personalized medicine, everything is sitting within the double helix. So Watson is still alive. Crick unfortunately died. I came to know both of them. And the double helix brought to the discovery not only of mutations, but also on the ability to read the DNA. Now we can sequence it. You know, the sequencing of the first human genome took about 7 years and almost $1 billion. Now we can do it within less than a few hours in about less than $5,000, and the price is still going down very quickly. And in the near future, every doctor will have a sequencer on the table, and he can do the sequencing even without taking blood, just by taking a buccal smear. And tell the patient, you know, have a cup of oolong tea. Once you are done, come back and I'll give you your sequence. So medicine changed accordingly. You know, until now, medicine was in a way what we call pajama type, or one size fits all. You know, why pajama? Because pajama, we are not going to the tailor for pajama. We are going to the store, and there are 3 sizes for pajama. Small, medium, and large. And in between, there is the rubber band, right? But we are moving from pajama type, we are moving to tailor-made. We are going to tailor the treatment to the patient. How? By sequencing the DNA. And by understanding the mechanism of the disease, which mutation the patient has. So, and the mutation can be different from patient to patient. So let's take, for example, just one example, breast cancer, okay? So breast cancer, here you have two biopsies. You know, if a woman has a lump in the breast, she goes to the doctor takes a biopsy. So you have two biopsies here. You have a biopsy A and biopsy B. So patient A, you see the cancer, it's one island, and here you see that the cancer is several islands. But what the pathologist manipulated the cancer in both patients. He stained it with an antibody. He did what we call immunostaining. And what did he do? He stained it with an antibody to the estrogen receptor. So you see that these islets stain and these islets don't stain. So this woman has a mutation in the estrogen receptor and she can be treated with tamoxifen. This woman has no mutation in the estrogen receptor, so she must have a different treatment. Because if I treat this woman with tamoxifen, I'm wasting time, I'm wasting money, because meanwhile she deteriorates. This is not the right treatment. This woman might have a mutation in the EGF receptor, in the HER2, and she should get another treatment, Herceptin. And another woman might have a mutation in the progesterone receptor. And another woman has a mutation in something else that we don't know. No estrogen, no progesterone, no EGF. She's triple negative, which is very bad because we don't know the reason. So you see that the same breast cancer, the tumor in the breast, can have different reasons. You know, think about a car, okay? It's very rainy in Taiwan, right? I came yesterday, it was horrendous. The plane couldn't land even because of the thunderstorm. We almost flown to Kaohsiung to land. So think about a car that you cannot turn on in the morning, okay? So the name of the disease, I cannot turn my car on to go to empty you to my lab. But the reason can be different. The reason can be that because of the rain, the sparks are wet. The reason can be that you forgot to put gas. The reason can be that you left the lights on and the battery is empty. The reason can be that you drove a bumpy road and a stone, you know, broke your oil tank and the oil leaked and the cylinder don't move in the barrels. So the name of the disease, I cannot turn on my car. But the reason for the disease can be different. And if you treat the disease with the wrong treatment, the car will still not go on. If you don't have gas and you change the battery, nothing will help you. The car will not turn on. The same here. So until now what we did, there was a tumor in the breast, we took the breast off. The surgeon mutilated the patient and took the breast off. So this is not a treatment, this is a mutilation. If we want to hit the reason, we need to understand the reason. And now we have molecular tools to understand the reason. And even if we don't have a drug, we can use computational chemistry in order to design a compound that will dock into the mutated protein and will inhibit it. So we have tools now. And we don't need even to crystallize the mutated protein. We have AlphaFold. We have all these programs, all this software that can model all the proteins according to the sequence and tell us where to go to inhibit the protein. So you see, we needed the technology in order to develop a personalized medicine. So we are developing now a bank. We are sequencing thousands of samples of each disease in order to understand the reasons for each disease. And there will be no 3 breast cancers, there will be about 10 breast cancers. 7 of them we know that they exist. We start to understand the reasons and we are on the way to develop new drugs. So that's the roadmap. Sequencing, understanding the reasons for all the diseases and developing drugs accordingly. And to go to the implications of this revolution on medical education. Now, for me as a medical student and as a physician, medicine has 3 pillars. Right? Disease, patient, and treatment. This is the 3 pillars of medicine. With the new revolution, this is going to change in a big way. The disease is going to change from this view of the old woman and the doctor that measures her pulse and the nurse that holds the baby crying around his mother, to molecular diagnosis. So let's say that somebody takes my DNA, and I'm going to come back to it, and sequences it, and finds a mutation in P53, which is a tumor suppressor, or in another gene, which carries high susceptibility for cancer or from other disease. So now the question is, am I sick or am I healthy? You know, until now, sickness or disease means that you cannot get up in the morning and go to school or to work. That's a disease, right? You say, oh, mom, I feel bad, I cannot go to work, I cannot do this, I cannot do that, or you call your husband or your wife. But a disease might be something that we don't know yet about, but it's already been cooking. So is it a disease or not? We don't have an answer. And the question is, in the eyes of whom? The eyes of the insurance company? The eyes of the employer? The eyes of the family? What does it mean that I'm standing before you now, thinking I'm healthy, but basically I'm cooking something in that may come out in a year or two? Is it a disease or not? So the definition of disease is going to change. Here, you know, we have biomarkers, and biomarker can be a mutation in the DNA. Newly developed blood tests can detect cancer 4 years before conventional methods. If I go here and find and screen you for biomarkers for cancer, and I discover that about 10 of you have biomarker for cancer, are you sick or healthy? Think about it. What about the patient? Patient is typically a sick patient. But maybe the patient can be the sperm or the egg. We can treat it before it's even fertilized. We can edit the genes that are not correct, that have mistakes. We have now gene editing technology developed initially by 2 Nobel laureates, right? By Emmanuel Charpentier and Jennifer Doudna. And now we have RNA editing even. We don't have even to go to DNA editing. And the technology is developing very fast. So who is the patient? The sick patient, 5 years before the disease, or maybe 50 years before the disease, or 60 years before the disease, treating the sperm or treating the egg. And the treatment can be gene editing. We don't need drugs. We don't need operation, because drugs and operation are for already developed disease, when we have the disease. But this treatment is to prevent the disease. So think about the shift that medicine is undergoing because of the knowledge and the technologies that we now have at hand. Now, let's go to the last part, and that, what are the prices of this revolution? So first of all, there will be a price in dollars. It's going to be very expensive. And why it's going to be expensive, and why the pharma companies don't like it? Because each disease is going to be sliced. You know, until now, when you have one treatment for breast cancer, and that's cutting the breast or giving irradiation, all women in the world are treating the same. But if now there will be 10 breast cancer, the cake is going to be cut into 10 pieces. And each piece will be different. Each piece will be different drug. And drugs have to be developed. And development of a drug is $5 to $10 billion. So the pharma companies don't like it. They want one drug for one disease. The same for heart diseases. You are not into it because you are not a medical audience at large, but I can tell you that until now there was one drug for cholesterol, statins. Now there are at least 3. There is an antibody, anti-CKS9, there is a CRISPR treatment, there is an siRNA treatment. Many treatments are coming to the market for the same disease. So it's going to be expensive, right? And expensive means accessibility. It will not be accessible to everybody. Even now, health insurance is limited. But the other issue is genetic privacy. Because the first thing that people are going to do is to sequence your DNA. And by sequencing the DNA, even before they come to a conclusion, they already have an information about you. They might have an information on malignant diseases, they might have an information on psychiatric diseases, on Alzheimer and so on. You can imagine a situation that I'm sitting and have a chest pain, okay? So I go to the emergency room and I ask the doctor, I have a chest pain, maybe I have a heart attack. So the doctor takes a sample of blood and he comes back and he says, Aaron, you don't have a heart attack, but you have a mutated APOE4, which predicts Alzheimer in 5 or 10 years. So what I'm going to do with this information if there is nothing to do about Alzheimer? I cannot treat Alzheimer. I cannot prevent Alzheimer. And to whom belongs the information? What shall I do with it? Go to my wife? Go to my health insurance? Go to my employer? Go to my children that might carry the gene as well? What do I do with it? You know, the ability of modern medicine, modern biology to predict is a time bomb. You know, we are living in a world, if you think about, if I ask you, what is the most important factor that protects us as people? Maybe some people in Taiwan will say it's the shelter that protects us from the Chinese. Maybe. I don't know about that. And for us in Israel, from the Hamas, from the Palestinian, maybe it's sophisticated weapons. No. The thing that protects us the most is the lack of knowledge of the future. The fact that we don't know what will happen in a minute is the most important fact that keeps our integrity, our personal integrity. You know, because we take many risks. In 2 days I'm going to fly back to my home. You know, the airplane may crash. An airplane crash. The statistics is low, but they nevertheless crash. But I take the risk because I don't know. Or you can take a car and there are road accidents, or we're exposed to pollution. The lack of knowledge of the future is something very important for us. This technology breaks this border, breaks the wall. It has the ability to make a prediction. And the question is whether we want to know the future or whether we don't want to know the future. It might not be in our hands. If you don't want to know the future, but the insurance company may want to know the future. Or the government that takes you to the military will want to know the future. Or even your spouse will want to know the future because you want to know how your children will look like. So once there is a knowledge, there will be someone that wants to know it, I can tell you, for sure. And the knowledge may leak out even, because computers can be hacked. Right? The genetic privacy. Be prepared for the big genome leak. It will leak out. And then one day, somebody will call you and you'll say, hey, Aaron, I know that you carry a mutation, and if you're not going to pay me $100,000, I put it on the internet. And it happens. People break into computers of hospitals, right? I don't know in Taiwan how protected you are, but they did break into the computers of my university. It can happen. So you see what's going on here. And then come also the public service. And this is Angelina Jolie. Angelina Jolie came in the summer of 2012 and said, I'm going to take away my breast and my ovaries. Wow! The most beautiful woman in the world is going to remove the symbol of womanhood because her mother had breast cancer and she died. And her aunt, the sister of the mother, had ovarian cancer and she died. And she gathered that she might be carrying BRCA1, BRCA1, a mutated gene that carries high susceptibility for both ovarian and breast cancer. And indeed, she did DNA testing and she was found positive. And therefore she decided to take this preventive step. Again, she removed a ticking bomb from her body. But what about the children? Not the adopted ones, the one that she has with Brad Pitt. They might carry the gene. So you see that technology always brings questions, but there are solutions. we are able to correct genes and so on and so forth, but we are moving there. And actually, if you walk into any hospital in Taiwan, they are already doing personalized medicine. We don't have the full knowledge, but they will test every cancer patient for mutation in order to predict the prognosis, the future, the efficacy of drugs. So we are already in. People ask me, oh, you're talking about the future, when it will happen. In 20 years, 50 years, maybe we will not be alive anymore. No, it's going on now. We have the technology. Every department of pathology, every hospital has sequencers. We are doing now DNA sequencing, and so on and so forth. So we are already in it. And we need to ready ourselves to the implications, to the price, to the ethical implications. But future medicine is going to be much more sophisticated, much more accurate. We are going to hit diseases directly in their mechanism and with much less side effects. Much less side effects, because we are going to have bullets that are targeting exactly the target. So this is the revolution of personalized medicine, and I think I'll conclude here. So thank you very much.
Thank you, Dr. Aaron Ciechanover, for the marvelous speech. 谢谢 Aaron Ciechanover 博士精彩的演讲。